from this tutorial 2.1. So yesterday somebody asked me which one should we do and how should we proceed. So the rule is very simple. So whenever we do something like tutorial 2.1, that means it's what I'm doing here in front of you, okay? And that's really to go through things together. And then the number, for example, today 2.2 is exercises for you to do on your own, okay? So typically in the 2.2, the first exercise will be go through some of the steps of the 2.1 just to make sure that everything was clear, okay? But let's say the first one of the afternoon is just something to illustrate some of the concepts, okay? Really, the exercise session is the second one. So that's what you're supposed to finish. So clearly, some of you may not have the time to finish everything during the hands-on session. That's fine, it's not a problem. But I would advise you to try to do as much as you can. And if you don't have enough time, try to finish when you have time in the evening. Again, you don't need to do everything, but maybe what would be good is to go through, taking a look at all the exercises, so you see more or less what we would like, to be able to do. Okay, even if you don't do them fully. All right. So just, suppose in the afternoon, in the evening, you didn't finish what you were supposed to do. At least read through the, let's say tutorial 2.2. Read through it to see what the exercise is about. So most of these tutorials are designed in such a way that the answer is already contained in the tutorial. So even if you don't run it yourself, you will see some plots, you will see some discussion, which is very useful. Okay? So that's the story. So now what we're going to try and do today is to discuss equilibrium structures. So in the same way yesterday we mentioned things like pseudopotentials and cutoffs, which we had discussed then this morning. So now we need to introduce concepts which we will see in more detail tomorrow, okay? Otherwise we are stuck at doing the same things that we did yesterday. So I think what I would like to do is to study essentially the structure of very, very simple systems. Again, the formal theory, we will do it tomorrow morning. What we need to know now, and that's the only rule we need to remember, is that when you want to find the structure, the equilibrium structure of an object using the FT, basically the prescription is the following. You consider all possible structures, and the equilibrium one at zero temperature and pressure is the one which gives you the smallest DFT total energy. Okay? So to find the equilibrium structure, what we do is to calculate the total energy for several configurations and pick the configuration which gives us the minimum. Right? So let's do an example for the simplest possible situation, which is a molecule. And now I'm considering the chlorine molecule. We could consider any other molecule. There is no particular reason. I mean, I picked one which was simple enough. So in order to discuss that, essentially what we need to have in mind is that the equilibrium structure of a molecule, which has two atoms, is quite simple, right? It's completely defined if you define the bond length, as simple as that. So finding the equilibrium structure of a molecule, the atomic molecule, means finding the equilibrium bond length. Okay? So that means we need to perform a one-dimensional optimization. We will calculate the total energy of chlorine and chlorine at different bond lengths and find the bond length which gives us the minimum total energy. So that's basically the procedure. Every calculation of equilibrium structure is done in this way in practice. Okay? This is the simplest possible example, so we start from that. So clearly, if we go for a chlorine molecule, we need to discuss chlorine atoms, and then we will need a pseudopotential for that, as we've seen this morning. So before getting to the pseudopotential, let me just create a new directory. So here I logged into the cluster already. Okay. So we create a new directory, which is, I don't know, Scratch, Summer School, Tutorial 2.1, okay? Then I go there. And here there is nothing because I just created it. And what I told you is that we would like a pseudopotential for chlorine. So in order to find pseudopotentials, remember there is this hyperlink you can follow. What I suggest is to stick to this pseudopotential here. You can choose anything you like. My suggestion to stick to this specific one is that this is the one I picked. So by using the same, we will make sure that we get the same number so we can all discuss the same things, so as opposed to have all numbers scrambled here and there. So what I'll do is to just try to get this, okay, and see whether we can get it. All right, I got that. And then here we continue. And the idea is that basically we need the executable as last time, a submission script, and a input file. So at this point, since we have some already prepared some stuff, we can just recycle it and then do modifications, okay? So for the input file, I'll try to find it. I don't know. I guess it was here in my case. Okay. So now, so the executable. So that is it. And now I need the input file for chlorine. In practice, the input file is already here, so I will just copy paste this one, and then I will explain what this is. So I do vi, I don't know, cl2.input, and I try to put this here. Then there is another bit on this side. And now I'm going to try to explain what this means, okay? So if I do more input file, I get that. So what this means, you always start the input file with this kind of keyword, which basically says to the code that you are starting a set of parameters defining the type of calculation. Okay, so this is calculation equal SCF, a self-consistent field. It means that we only calculate the total energy of the system, okay, with the nuclei so fixed in some configuration. We will see tomorrow as an example where actually you can do other type of calculation where the nuclei can move. So this is just the name of the output files we are giving, just a tag. We have the pseudo potential in this directory. We are asking for the output to be also in this directory. Now, what about, so how do I place the chlorine molecule? That's exactly similar to what I showed you for the water molecule in the morning. So you have basically a molecule in a box, all right? So the easiest thing is to put a molecule in a cubic box and keep it further enough away from the other replicas. So maybe let's check what this iBrav1 means. Let's see whether so instead of just listen to me, we can also check directly. So there should be some documentation somewhere, and there should be some, I don't know, documentation somewhere here, I suppose. No, that's a mess. So let's do this thing. Input pw.x. I don't like it. So we can go here. And that's basically the file that I was mentioning yesterday. Okay, so the page where you see all the input variables. So what I wanted to check is how to make a box, which is a cube, and where I can place a molecule, okay? So I told you that the choice of the lattice is here. That's basically an index of the Bravais lattice. So if I look for iBravais, is it here? I click on it. So I can read through this thing. So what it's telling me, basically, is all the possible choices of this index, which specify different lattices. Since I just want so yesterday we used silicon, okay, which was a FCC, okay, so this one. And today we would like to have a cubic structure for chlorine. So I'm going to put a molecule in a box, which is cubic. So I need to go for this flag. So iBrav equal 1, okay. So that means that the lattice vectors will be lattice parameters times 100, then 010, and 001, all right? So here we are having iBrav equal 1, and there is only one variable. So if I go here as well, you will see that if you specify these lattice parameters, what you need to give is only, so where are we? Here. You only need to specify basically the this number, cell dimension number 1, which is basically the lattice parameter. So in this case, I'm setting this equal to 20 in atomic units, so that's in Bohr, okay? So that's about 10 angstroms, because I expect the chlorine molecule to be of the order of maybe 1-2 angstroms in bond length, maybe 2. So we're going to have one chlorine molecule, and then the next one is going to be about 10 angstroms away, okay? So they don't interact. So how many atoms I will have in my system? 2 atoms, so 2 chlorine atoms. how many types of atoms, one because it's basically only chlorine. And then here this is the cutoff that we discussed this morning. So in the tutorial, so in yesterday's tutorial, the exercises, there was an exercise where you were asked to find the converged cutoff for silicon, okay? And there was, I don't know, something like 25 Rydbergs, okay? So if you've not done that, it would be useful to do it. So in this case, since I don't want to spend too much time on that, I did this convergence on my own, so when I was, before coming here, and I found that a good parameter, which gives the accurate values, is 100 Rydbergs. So that's already, essentially you can take it from me and we can continue. So this is not very important, but it's just a way, so this flag has to be here by default in the code. And this is just saying that when you do these iterations to find the total energy using this self-consistent procedure, so density, potential, Schrodinger equation, wave function, new density, and so on, the criterion to exit the loop, okay, is that the total energy differs in relative terms from the previous one by 10 to the minus 8. If you basically have 8 significant digits which don't change anymore, you exit the loop, okay? So that's what it means. That means that if you here you write down 1.0 d minus 14, you have many more iterations, your number will be more accurate, but in practice for what we are doing is fine, okay? So which atomic species we have? So it's chlorine, this is the pseudopotential, and this is the atomic mass. Now, one may wonder why I'm placing the atomic mass of chlorine to 1. There is no particular reason. It's just I was too lazy to look at the periodic table. The point is that if you think about it, the total energy of two molecules or two atoms being a certain distance, it cannot depend on the masses. The masses only affect the kinetic energy. If the nuclei don't move, the mass doesn't matter. So if I put there 1 or 1 billion, it's the same. So the numbers will be the same, right? So when we do static calculations where the atoms don't move, the mass is irrelevant. Only when you allow the atoms to move, that becomes an important parameter. So the positions of the atoms here, this keyword here says that I'm specifying them in Bohr, okay? What I'm choosing basically is a configuration where the first atom is at the origin of the frame, so 0, 0, 0. And the second one is basically at 2, 0, 0. So basically, the first atom is in the center, is at the origin of the box. The second is displaced with respect to this one along the x-axis by 2 Bohr. That's about 1 angstrom, okay? So that's one choice one can do. So I think we are kind of ready to do that now. So what we should do now, basically, we have the input file, we have the pseudopotential, we have the executable. At this point, we need to wrap this up into the submission script, okay, and submit it. All right. So since we're going to do this several times, today I'm going to go for a slightly different route, which is basically running interactively, so without the submission script. You can choose to run interactively, as was described in yesterday's tutorial, or by submitting a job. I recommend submitting jobs so that you get kind of an idea of how really things are done. But for very small calculations and to do things lively here, I'm going to do interactively. Okay. So nothing changes. In practice, if you remember yesterday, we had this submission script. Okay, you remember that? So running interactively means that one opens an interactive session. You have the commands in the previous tutorial. And at that point, you can just type this to get your calculation going. Okay. So now I already started an interactive session just before starting the this kind of discussion. And that's just to go a bit faster so we can have a discussion in a bit more, kind of lightweight session. So what I'm going to do now is to basically run this operation. Let's say, I don't know, 12 CPUs, pw.x. I don't need to specify this number. So this is something we will discuss maybe a bit better tomorrow. And then
can you just remind us what's the M-forming?
Yeah, I wanted to talk about that tomorrow. It's okay, since you ask now. So today, basically, we introduce the concept of K-points. Okay. So basically, suppose you have 100 K-points. You can actually split them across CPUs. You can say the first CPU gets 10 K-points, the second one gets 10 K-points, the other one 10 K-points, and so on. All right. So that's so N pool. So means in how many groups of CPUs, you want to split the number of K points. All right? So that's the meaning. So for now, we don't need to worry too much. I mean, that's something I will like to discuss maybe tomorrow, after tomorrow, when you do something more complicated. For now, it's not a big problem. So in this case, basically in the input file, we are specifying K points. So instead of K points like 444,000, you see that there is a keyword called K points gamma. So gamma in solid state physics is the K equals 0 point. So there's only one K point, and that's because it's a molecule, it's not a solid, okay? So we don't want to put a wave vector. We don't need to describe a solid. So since there's only one K point, I don't want to use several CPUs, so to spread this number in several CPUs, otherwise it's going to crash the system. Actually, maybe we can try. So if I try to run this thing using several CPUs, the system, so by splitting the K points across several CPUs, the code is not going to be happy, because basically it's going to say, I have only one K point, and you are telling me to split them across two CPUs. All right? So that's not going to work. So when I run interactively, I may also look at the output as it goes through. I don't need to pipe into a file. So typically, that's what you obtain. Okay. So that's basically a typical calculation. And you can see basically we obtain something out, total energy, and so on. Okay. So this is basically just to test that everything is fine, that we have some numbers, that with this distance we have a certain total energy. Okay. But this is a calculation with a static configuration, basically two chlorine atoms sitting 2 Bohr apart. Okay. That doesn't tell us what is the minimum energy. So to find out the minimum energy, what we want to do is to perform several calculations at different bond lengths. So you do small bond lengths, you increase, and then you do a plot. As simple as that. I mean, there is really, and that's most of what is done in DFT. Then people do it in a more systematic way. There are some tools to do it better, but that's the core concept. Okay. So what I want to do now is to generate input files for different bond lengths. Okay. So the way to do it in practice is to do something like go into this file, change this bond length, maybe 2.2, 2.4, 2.6, generate files, and then run all of them. Since this is a bit boring, at some point you learn how to write a way which does this operation for you automatically. So that is basically a little tiny script which can do this for you. So I will not explain every bit of this script because it's kind of a geeky thing to do. But it's basically a way which we replace the number 2 in your file, but all these numbers, 2.2, 2.4, 2.6, and then create output files with a label telling you the bond length. Okay. So that's just a way not to do it by hand. If you want to do it by hand, just do it by hand. There is absolutely no problem. This is mostly for me because I don't want to change numbers in front of you now. It's going to take an hour. So when we do that, basically, so I'm going to just copy paste that and I put it in the script which we call, I don't know, something dot. So my script.tcsh. Okay. So I just copy paste that. So let's see if the name is the same. So is reading this file and is expecting this label. So I have this file, and I should have the 2 point not here. So let's see if it's going to work. If I do that, so that is a script which has to be run using a program called tcsh. That's called is a TC shell. Okay, it's just a tool available on these computers. If you do that, it seems to have done its job. I do ls. So you can see I find this file, this file, this file. Maybe if I open one of them, I will see that here I have 2.2. So there's 2.4, 2.6. All of them are the same, basically. Okay. So what I can do now is to run the same operation for each of these files. So as simple as that. And the way we can do it is maybe to try to do it by hand brutally. So I can do that 2.2.in, and I'm going to pipe it into 2.2.out, right? So hopefully this is going to go. No, it's not happy because I have twice this thing, right? So now it should go. So that is done, hopefully. So if I do that, I have something out. So it finished, okay? So what I need to do now is the same, but for all of them, 2.4, 2.4, and so on. So sorry guys, I really need to do it for all of them. Then 2.6, 2.6. Okay, so maybe I'm not going to do all like 20 of them, otherwise you're going to kill me. But what we can do is that at this point, what we want to know is the total energy in each case. So if you remember, the total energy in each output file is the last value called the total energy. And to distinguish from previous things where there is also total energy, people writing this code were smart and say, okay, let's put an exclamation mark just to make sure that you know which one it is. That's useful because now if I do use a command which is grep, okay, and I look for this symbol into, let's say, this file, the output file, it's not happy. Maybe this one. Okay, so basically this extracts the entire line which contains this character. Okay, so in this case, for this file where the bond length is 2.2 Bohr, the total energy is like minus 57.5 blah Rydbergs. Okay, so what I need to do is the same operation for 2.4, the same operation for 2.6, 2.6, and so on. Okay, so for each of these, I will obtain a value of the total energy. Okay, so in practice, what happens is that, so I will not run all of them, but what you will get is that if you have all the files basically written down, you can do a search of this exclamation mark using the wildcard here. So you will just go through all of them. And as output, you will see basically the same line I showed you before, but for all of them, 2.2, 2.4, 2.6, and so on, okay? You have this object here. So let me just copy. No, that is not going to work because it doesn't copy properly. But basically, if I had all these numbers, then what I can do is to use a command called gnuplot. So if I do something like that, gnuplot, okay? And at this point, I can try to plot this file, I don't know, with this name, using first column, second column, with lines. So the specific commands to do the plot, you will find them in the tutorial, okay? So we don't need to go through them. It's just a bit, it's a little program to plot data. It's not really difficult. And the specific syntax you will find on the tutorial. So what I want to show here is that if you put this data together, you basically find this plot, which basically I found precisely by running all these calculations, okay? So now we did 2.2, 2.4, and 2.6. So if you continue all the way to 4.6, you get all this data. And what I did is a plot of basically this number, 2.2, 2.4, and so on, versus this number, okay, the total energy. So what you find basically is this. So that's obtained, using gnuplot on this on the machine. So what you find basically is the black dots, okay, and this line is just a kind of a basically a spline line, to fit through them. Okay, so the idea is that from this plot, what you can tell is that there is a certain equilibrium bond length which corresponds more or less to this region. So clearly here, this is very, I'm trying to eyeball it, but in practice, you can zoom into the figure, you can tell exactly what is the equilibrium bond length. So let me just discuss the result. Basically, if you zoom into this figure, you find basically 1.97 angstroms for the chlorine bond length in the FT. Okay, so if you take the experiment, that's 1.99 angstroms. Okay, so the point is, or this exercise is to show that essentially you underestimate the experimental bond length by about 2%, 1 to 2%. Okay, so that's actually very typical of DFT LDA. It gives bond lengths which are slightly shorter than in experiments. That's a very typical thing, but they're quite close. They're always maybe 1-2% lower, not very far from experiment. So that's why these things are quite popular, are very popular, because it's it gives you something which is very, very close to experiment. And here the only input parameter really is the atomic number of chlorine. So we're talking about something completely from first principles. Okay. So now what I would like to consider is a slightly different property, which is the binding energy. Okay, so basically the binding energy is the energy which you need, or the dissociation energy is the same. The energy that you need to form, so basically the energy that you gain by taking two atoms and putting them together in a molecule. Okay, that's the same as the energy that you need to break it apart. Okay, that's quite a standard thing in chemistry. And since we have the equilibrium bond length here, what we can do is to compare the energy of this molecule at equilibrium with the energy, with twice the energy of a chlorine atom. Okay, so what we need to do now, so since here you see we have, I don't know, 3.4, 3.6, 3.8, the minimum is not maybe one of the points that we have. So it is useful to rerun a calculation with this equilibrium bond length that we determined. Okay, so what I'm going to do is to just maybe take this thing here and use the equilibrium bond length that we just determined, okay, and run it again. So if I do that, okay, so you will notice that by doing basically up arrow, I go through the commands of the previous, so that's very useful. So if I do that, basically, I'm running again this story. And then if you look at the energy, that is basically the total energy of this system in the equilibrium configuration. Okay, so that's a number. That's one of the two things that we need. The other thing we need is the total energy of a chlorine atom in isolation. Okay, so we basically need to generate an input file for the chlorine atom in isolation. Now, this seems trivial. It is not. So the reason is that when you look at one chlorine atom, what you're going to find is that in the, if you can see that, so basically in the 3p shell, you have basically two electrons basically with compensated spin here, the same here, but one of the orbitals has an ampere spin. Okay. So that's a bit more of a complication. So we need basically to run a calculation which is a bit more complex. It's called a spin polarized calculation. So it's a calculation where there is not just an electron density, but there is also a spin density. So the number of electrons which spin up can be different from the number of electrons which spin down. So what you see here in the tutorial is that the input file is almost identical to what we had before. So everything that is in black is exactly what we had before. And the red is what has to change to study one atom. So what I'm changing basically is the fact that I only want one atom now, not two. Okay. I'm telling the code that I actually want to consider two spin orientations. Okay. And I want the system to have essentially a spin 1/2 configuration. So that's basically in terms of Bohr magnetons. These two keywords are there in order to essentially make sure that the system converges. So unless you are burning, you have a burning desire for me to tell you what that is, I will skip it gladly because it's more technical. And basically at this point, we have only one atom, and we can let it at the origin of the frame. Okay. So let me just bring this on the other side. So I'm going to call it chlorine.input. Okay, I have that, and then the other part, which is here. Is that, and what I need to do now is to run this object. So is this new guy. So let me just record this number. So that's the total energy of the chlorine molecule. And now we have the chlorine atom. So again, it runs, and at some point it should give us some kind of total energy. And the result is here. So that's basically the total energy of a one atom of chlorine. So I'm going to do something like that. Okay, and hopefully, yeah, this is not going to be happy. Sorry. If I want to calculate total energy of chlorine minus twice the total energy of the chlorine atom, I get this number. So this number is in this case is Rydberg's. So one Rydberg is half a Hartree. So it's 13.6 electron volts. So if I do that, okay, is about 3.57. Let me check this, okay, yeah. So here I had written down 3.58, okay. That's basically the dissociation energy of the chlorine molecule. So energy of the molecule minus twice the energy of the atoms. So if you compare to experiment, actually, basically you can break this molecule with a laser, basically, by pumping enough energy. So in experiment, that's about 2.5 electromoles. So this actually is quite a common trend. Basically, what you get in DFT LDA, local density, is that the equilibrium bond length is very good, okay? But the dissociation, so let's say the binding energy is too strong, basically. It's about, here you can see it's about 1 volt too strong. So that means that the potential well, which defines the equilibrium structure, is too deep in LDA. That's a common trend which applies to many materials in practice. So that's very representative of what people find. All right. So just to give you an idea, that's something that is in the exercise on Friday afternoon. So the last one, we will basically make a calculation with a PBE. So this thing, another flavor of exchange and correlation. So PBE became famous because in practice, instead of having an error of the order of 1 electromoles on the binding energies, they managed to reduce the error to maybe 0.1, 0.2 electromoles. So that's why it's very, very good for many properties, while maintaining the accuracy on the equilibrium structure, so bond lengths and things like that. Okay. So basically, that's what I wanted to tell you about chlorine. So now what we can do, we're going to try to do it a bit more quickly, is to go through a bulk crystal, because that's what I would like to do during the exercise. So let's take again silicon. And the idea here is very simple. In the case of a molecule, we are optimizing 1 degree of freedom, which is basically the length. Okay. In the case of a crystal, suppose silicon, we have 2 atoms in the unit cell, but we don't need to sweat too much because we already information from experiments telling us that you have FCC lattice, Wyckoff sites are very well known. So what we can try to do is to set the experimental symmetry, okay, and just ask what would be the lattice parameter. Okay, so it's again a one-dimensional optimization where we want to determine the bond length of silicon or the lattice parameter equivalently. So the idea is to create unit cells of silicon with different lattice parameters and calculate total energy and see what is the equilibrium, basically bond length. So maybe I can copy paste this, which is basically the same that you had yesterday. Okay, let me try to do this. So I'm going to move in a new directory so that it's a bit cleaner. So it is called silicon.in in this case. So the input file is always the same: self-consistent field calculation, name of the calculation you want, the name you want to give the calculation, where you find stuff when the code has finished. In this case, iBrav equal to was a FCC lattice. This is the equilibrium, so the experimental bond length. Sorry, experimental lattice parameter. 2 atoms, 1 type. That's the cutoff that you should have determined yesterday using by a convergence test. The silicon atom, the pseudo potential we already found, and the 2 Wyckoff sites. Okay, and this is basically a standard setting for the discretization of the Brillouin zone.
The 111 means what?
The 111 is something that you should know what it means because it was one of the things discussed in the tutorial yesterday, tutorial 1.2. So that means that yesterday night you did not spend time doing the tutorial. No, basically it means that. Sorry, I'm joking. It's okay. You are forgiven for today. So if you go to tutorial 1.2, essentially, one of the exercises was to try for silicon a situation where you do a convergence over the number of K points using 0, 0, 0 everywhere, or repeating the same operation using, 1, 1, 1, like 4, 4, 4, 1, 1, 1, and things like that. So that's precisely what you're asking, okay? So if you do that, so the idea was that by doing this calculation, you can discover by yourself what this is doing. In practice, what it does, 0, 0, 0 means that so if you have a, basically in 1D, so if this is your unit cell, okay, so brilliant zone. Suppose you have a one-dimensional brilliant zone. Let's say 4 means that you are splitting this in 4 bits. So your points are 1, 2, 3, and 4. Okay. So in 3D, 4, 4, 4 would mean this in 3 directions. Okay. So when you do 4, 4, 4, 1, 1, 1, what this means that actually you take this same partitioning, but you shift everything by half a bin, if you want. So one could say why this is useful. Well, the answer is in the exercise which was planned for yesterday, basically. So what you can see is that if you take the one with 0, 0, 0, it's called unshifted, the convergence is quite slow. If you take the shifted one with the 1, 1, 1, you converge extremely fast with the number of points. So the reason for that is that in the brilliant zone of a crystal, not every point is created equal. So some points are much more important because essentially they because of symmetry, they are repeated more time in the brilliant zone. So if you capture those points, you describe more. You basically are capturing more information. So it's just a way to discretize the brilliant zone. And if you shift it, so if you use 1, 1, 1, you probably can converge faster. That's standard thing. Okay. So if you really want details, that's you have all the numbers basically here. Okay. Does it answer the question?
Yeah.
Okay. Good. So let's try to go back where we were. So we were basically looking at silicon here. Okay. So the idea basically is that we have this thing. So we need the executable from somewhere. Okay. We need the pseudo potential again that I guess we can find from the first tutorial. Okay. So we have everything. So at this point I can run again interactively this thing. So I should do maybe at this point I can keep it like that. Maybe I can do that. If I do this, I get my calculation. That's just to make sure that everything runs. I get the total energy and so on. So this is the starting point. Now what we should do basically is to basically take the lattice parameter here, okay, and change it. So if you look here, so these are given essentially in crystal coordinates. So if you expand the parameter, they move with that. So you don't need to worry about that. So the important is to change this number. Okay. So the idea is to do exactly the same thing that we did for chlorine. Okay, but changing this lattice parameter, do, I don't know, 10, 20 calculations, and trying to be around maybe the experimental lattice constant so that you don't look at something irrelevant, and then trying to plot the result. So since I think we are running slightly over time, I want to show you the result. So the operation is identical. You basically try to create several files, either manually or using this little script. Okay, it's your choice. Then you try to run all of them sequentially. So 1, 2, 3, all of them. And at that point, you grep for the total energy. Okay, so the result is for each lattice parameter here, you will have a total energy. And then you try to use a GNU plot to perform a plot of the result. Okay, so what I obtain is these black dots here. So what you can see is that basically we have equilibrium around this point. So if I zoom in, what I found is that my equilibrium lattice parameter is 10.2094 Bohr, which is 5.403 angstroms. So in experiment, you find you have 5.43. So that means that if you take the ratio, the DFT-LDA is underestimating the measurement by 0.5%. Okay, so and again, this is a calculation from first principle, so there is no parameter. Okay, so that's why it's interesting because it's based on all these theorems, pseudo potentials, and all these things, you can get something which has absolutely no experimental input apart from the symmetry of the crystal. So what is interesting to know is that even if you remove the symmetry, if you start from scratch and try to look at all possible phases of silicon, you find that the lowest energy phase is the FCC structure and the equilibrium bond length is this one. Okay, we're not doing it just because it would take much more time, but that's basically what can be done. So if you perform the same operation we did before for silicon, so what you can take the energy of the unit cell, contains 2 atoms, subtract twice the energy of a silicon atom alone in isolation. So that's what is described here, basically. And again, you have to consider spin polarization, because in silicon we have a 3s2p2. And by the Hund's rule, you have to put basically 2 electrons spin up in the p orbitals. So that would be basically the configuration of the p states in silicon. So that can be enforced in the same way as we did for chlorine. The only thing that here now is a spin 1 configuration, because it's 1 half and 1 half. So that calculation will give you the total energy of one silicon atom. And from that, you can do the difference. So the energy of bulk silicon, which is 2 atoms per unit cell, divided by 2, minus the energy of 1 atom of silicon, you get this result. And that's basically 5.36 electron volts from the calculation. If you look at the heat of sublimation of silicon, okay, the measured one, that's 4.62. So basically, again, you have an overestimation of the order of 1 electron volt. A bit less, but it's pretty much the number. So also in the case of solids, basically the bond length, so the lattice parameters are very good, but the cohesive energy, so the energetics, so basically in LDA things are a bit too tightly bound, okay? That's a very, very standard trend, all right? So here we're talking, so I'm just looking at the relative error, and that's about 16%. So these kind of numbers are reasonable. That's pretty much what is not a unique case. In most cases, you get something like that for semiconductors, oxides, metals, and things like that. Okay. So the situation becomes a bit more tricky if you're looking at slightly more difficult systems like layer systems. So in the hands-on session, you will be asked, I think, to look at a system which is a bit more intriguing, which is basically graphite. So in the case of graphite, basically you have a layer structure. So it's basically graphene layers stuck on top of each other. And what you will see is that the bond length, so the lattice parameter in the plane, let's say in the graphene plane, is almost perfect compared to experiment. But the interlayer separation, that's is much more tricky to get right, basically. And that's because essentially there is very little electron density in the middle. Okay, so that's the operation. Now the other thing I would like to show is that in the hands-on session, I ask you also to try to run this software. Okay, that's basically a very simple visualization software to see structures. Okay, there is nothing really complicated. It's just to have an idea of what you are calculating. So this is something which is already on the cluster. So we had the guys install it for us. So if you do module list, that says which kind of software you have available in your case, and you should see this thing here. Okay. So we actually made sure that this is here when we modified this file yesterday at the very beginning. Okay, so we included that by having this thing in this file.bash rc. Okay, so you should see this when you type module list. If you see that, you should be able to visualize something. So let's maybe try. I mean, so this might have some problems in the sense that it's graphics. So we are exporting graphics all the way from Johns Hopkins, and it's a lot of information. So text is just a few bytes of information. If all of us start importing graphics, it's going to be a lot of information. So we discuss a lot with them about ways to do it, speedier. But as for the login, we never know what happens when you have 30 people connecting together. So this, you just type XTXDen and it starts. So what you will see basically in the tutorial sheets is all the steps needed to run these things. Okay, so you are guided through this thing, and in general you should see a window, and this window should have something, and you should be able to use it and to go through the menus and all these things. So now I'm on EduROM, so that could be slower than everybody else. But if you are on Cornell network, that should be much faster. Okay, so typically one opens a file, and here essentially the point is that you can open a file in the format of the input file that we have. So maybe you can try to open something which, I don't know, silicon.in. He's asking me for some stuff. I don't need to worry about that. I don't need to worry about that. And he should give me something which looks like basically silicon. And here, I mean, I'm not going to spend time on that, but you can play a lot and you can add bonds and things like that. And essentially, we will use that to visualize structures, but also to look at the electron densities, charge densities, and other things, okay? So today is going to be the first time you encounter this software, but you will see it's really, really very simple and intuitive. There is nothing really difficult. So I would say that we stop here now, okay? And then in 10 minutes, you can, or in 5 minutes, you can start the hands-on session. All right. So if you haven't finished what you did yesterday, I suggested you try, but don't spend too much time on that, because then if you spend 2 hours finishing what you did, was supposed to be done yesterday, I mean, it's not going to be interesting because you don't do the interesting stuff. Okay. So actually, I would be more keen on you trying the new stuff, because actually it's much more exciting and it starts to get interesting. Let's say. Okay. Okay, guys.